Good evening and welcome. I'm Chris McGann and I'm the Dean of the College of Sciences. I'm so glad all of you could be with us this evening. I know traffic was terrible getting over here. So State of the Sciences is the signature event of the College of Sciences, which celebrated its 5th year anniversary this past summer. Back in 2013, the reorganization at the university level created this college and brought together programs in the physical, chemical, mathematical, statistical, biological, and earth system sciences. Much of the rationale for creating the college was to enhance collaborative opportunities for students and faculty. This multidisciplinary convergence is key to addressing many of the world's greatest problems and helps spark the kind of creative thinking that our speakers will discuss today. Here are some highlights since our launch in 2013. We've awarded almost 5,000 graduate and undergraduate degrees to some of the nation's top scientists, young scientists. Our talented faculty have landed more than $183 million in research awards. And thanks to big gains in fundraising, we've more than doubled our endowment, growing by more than $28 million since 2013. These are remarkable accomplishments, and so give yourselves a round of applause for these 5 years. And thank you all for all your hard work. Before introducing our speakers, I want to recognize Dr. Mary Watson, Dean of the College of Natural Resources. You can wave. Thank you for being here, Mary. I appreciate that, your support. I also want to recognize the College of Sciences alumnus, Joe Bridger, for his generous gift that made this event possible. Joe's gift established the Spirit of Science Illumination Fund to support transdisciplinary initiatives and programs such as the one you are attending this evening. Thank you so much, Joe, for everything you do for our college. And now I'll introduce our speakers. Michele Root-Bernstein received her BA from the University of Pennsylvania and her PhD in history from Princeton University. She studies creative imagination across the arts and sciences, with particular attention to the thinking skills common to all disciplines. She has taught history, writing, creativity studies from grade school to college levels. She is a Kennedy Center teaching artist and an adjunct faculty member at Michigan State University. Robert Root-Bernstein received his AB in biochemistry and his PhD in the history of science from Princeton University. He did postdoctoral work at the Salk Institute for Biological Sciences, where he was awarded one of the first MacArthur Fellowships, commonly known as Genius Grants. A professor in the physiology department at Michigan State since 1987, he studies the evolution of physiological control systems and autoimmune diseases, as well as science-arts interactions. Together, the Root-Bernsteins are co-authors of Sparks of Genius, the 13 thinking tools of the world's most creative people, and numerous articles on imaginative thinking, polymathy, and transdisciplinary education. We are delighted to have them with us tonight. Please welcome Michele and Robert.
Thank you very much. We're very pleased that those of you who are here were willing to come in out of that beautiful sunshine outside to this dark little room to hear us. So thank you very much. We're going to talk to you about polymathy. You can also say it polymathy. There are two ways of saying it out there in the world: creativity and the Y-shaped student. So we propose to provide you with the highlights of our last 30 years of research into creativity. Because we're only giving you a taste of our findings, please feel free to ask us afterwards any questions you may have. We'll be bouncing back and forth between individual exemplars and large-scale statistical studies in order to give you a sense of how individual experiences of creative strategy and productivity are reflected in the data and vice versa. We'll define what we mean by polymathy and then flesh out our thinking with 6 themes that have characterized our research. So the first is creative individuals take on multiple interests and either vocations or avocations or both. The second is that creative individuals integrate their multiple interests. Third, some typical avocational patterns emerge, which we'll talk about. Fourth, perceptions of connections that polymaths make between their various interests and activities. Fifth, the ways in which polymaths cross disciplines, and we'll focus here on what we call thinking tools or tools for thinking. And sixth, how these thinking tools are used in professional practice and educational preparation. Seventh, we're going to conclude with educational implications. And here we're going to introduce preparing students for what we call a Y-shaped student and how that will lead to creative contributions. All right, so let's start with polymaths. Polymaths are generally defined as people of unusually broad learning and accomplishment. Leonardo da Vinci is obviously a prime exemplar: painter, sculptor, architect, musician, scientist, mathematician, engineer, inventor, anatomist, geologist, cartographer, botanist, writer, and not listed on this particular slide, professional juggler and gymnast as well. Obviously, this incredibly broad range of developed talents is beyond the aspirations of most of us, and yet we're going to argue that it's still possible for almost anyone to be a polymath without being a genius of the Leonardo type. Given our studies of all sorts of creative people, polymathy for us denotes something a bit more common, which is an active engagement in multiple interests or endeavors, mixing vocations and avocations simultaneously or serially at some point in one's lifespan. So we use the active at the head of our definition to signal the difference between a polymath and a dilettante. The polymath actually makes things. He or she is actively engaged in discovering ideas or relationships and possibilities, so that what we're really talking about here is creative polymathy. So theme 1 takes us back to our first days as newly minted researchers. As a graduate student in the history of science, I had occasion to read just about everything that was written by J.H. Van Hoff, who was the first Nobel Prize winner in chemistry. In 1879, he made a speech in which he described how his informal reading of several hundred scientific biographies led him to believe that imagination plays a role both in the ability to do scientific research as well as in the urge to exploit this capability in other ways as well. Moreover, he claimed that the most important scientists almost always express their creativity through arts, music, poetry, other forms of fiction, or philosophical and religious investigations as well. Significantly, Van Hoff himself played the flute extremely well, wrote poetry in 4 different languages, made models of many different kinds, and enjoyed sending out hand-painted New Year's cards. My subsequent involvement with a project carried out during the 1970s and 80s with the psychologist Bernice Ideson of UCLA started because my mother was her research assistant, and it allowed me to investigate Van Hoff's proposition further. The Ideson project was a 30-year-long psychological study of scientific careers and involved 40 early career scientists, all male, who volunteered to undergo regular psychological testing and interviews. 4 of these men eventually won Nobel Prizes. 11 were inducted into the National Academies of Sciences. 3 of the study subjects ended up in industry, and the rest had fairly typical academic careers. Contrary to expectation, initial data analysis found no correlations at all between the psychological tests and any kind of measures of scientific success or eminence. Scientists are a very diverse group of people. However, after Dr. Ideson's death, my mother and I took over the project, and I found some very interesting correlations between avocational activities, such as participation in the arts and music, and high-level athletic activities that did correlate, just as Van't Hoff had proposed. So I soon realized that neither Van't Hoff nor Ideson, nor we, in fact, had been working in a vacuum. Scientists, psychologists, and even historians of science have repeatedly rediscovered that very successful people in all fields are, to paraphrase R.K. White from 1931, not only more versatile than the typical college graduate, exploring a wider range of disciplines and activities than they do, but also more accomplished at that wide range of activities. The contributions that Michele and I have made to this line of research have focused in part on studies of Nobel Prize winners and their avocations. We documented that the more eminent the scientist, the greater the number of adult arts and crafts avocations they tend to have. Nobel laureates average one arts or crafts avocation. Only 60% of Royal Society and National Academy members had such an avocation, and in the average scientific community, such as Sigma Xi or the US public, it's about a third. These differences were highly statistically significant. Eminence also correlated independently of the arts and crafts avocations with lots of other avocations. So this raised a serious question. These eminent scientists appeared to be wasting, if you want to think about it that way, their time at non-professional activities, and yet they were significantly outperforming their professional peers. How does that work? Were such broad interests generally characteristic of creative people across disciplines, as the literature was indicated? And if so, why? So, while our initial Nobel studies focused on scientists, we are now completing a study of all the Nobel Prize winners in all categories: sciences, literature, economics, and peace. And this is what we found so far. As a group, all Nobel laureates pursue a wider range of subjects than the typical person, just as R.K. White suggested. At least half of the Nobel laureates have 2 or more areas of interests, and in fact, the average number of interests among Nobel laureates ranges from a low of 1.9 among the Peace Nobel Prize winners to a high of 2.8 among literature Nobels. And you'll notice that what we're talking about are things as different as sciences, humanities, arts, sports, and things like that. So these are very, very different areas of interest. However, interests vary quite dramatically from one group of laureates to another, a point we'll return to a bit later in our talk. The point now is that most laureates, regardless of their field, are more likely than the average person to display interests and accomplishments in multiple areas of interest. And now we're going to play tag team.
Yeah, so that brings us to theme 2. And now we'll look at a few case studies that tell us a little bit more than some of these statistical studies. Now, diversity of interests displayed by eminent individuals, such as Nobel Prize winners, is important. But so is the fact that these successful individuals usually integrate those interests in novel ways to produce new ideas, inventions, and innovations. Alexis Carrel, who won the Nobel Prize in 1912, made his breakthrough by integrating formal training in lace making and embroidery with surgical experience to invent the stitching techniques that make possible today the correction of aneurysms and even organ transplant operations. Dorothy Crowfoot Hodgkin pioneer in X-ray crystallography, also integrated her multiple areas of interest. Hodgkin was an avocational artist throughout her life, vocational if you count the drawings she executed for her archaeologist parents as a teen. Not only did she decipher the protein structure of insulin, she painted it. You can see that there. The same integration of interests was true for the Peace Prize laureate Dag Hammarskjöld. Hammarskjöld combined his vocation as a statesman and as UN Secretary General with multiple avocations: mountaineer, philosopher-writer, amateur photographer, and poet. Those avocations appear to have given Hammarskjöld needed insight into his political activities. He used mountaineering, for instance, as a metaphor for diplomacy, photography as a metaphor for seeing beyond the obvious. 2, he felt a great affinity for Barbara Hepworth's sculptural single form, and he wrote to her of his desire to, quote, model in action and words what she, Hepworth, was so fortunate to express to perfection visibly and tangibly in plastic form. The kind of integration of interests we see in the work of Carroll, Hodgkin, and Hammarskjöld have been noted more generally. For instance, the art historian and philosopher John Dewey noted the integrative drive behind the creativity of great artists, calling this aspect of their creative process the formation of integrative activity sets. Working on case studies in science, Gerald Holton, Howard Gruber, and Bob, too, have described the same idea using other terms, noting that it is the integration of activity that enables scientists to juggle multiple interests, to weave something new and more useful from independent threads, in effect, to create. Without the integrative weave, the polymath is not a polymath, but a dilettante. Indeed, as psychologist and historian of science Howard Gruber pointed out about Darwin, it was not that Darwin studied geology, geography, paleontology, anthropology, botany, zoology, and ethology, and was one of the first people to use the camera as a scientific tool. It was not this range of interest that made him great, well, not maybe, but that he synthesized all of these studies into a coherent theory of evolution by natural selection. Now, if avocational choices of Nobel laureates fascinate us, the avocational patterns of Nobel groups also surprise. You'll remember we mentioned that laureates have multiple interests and that these interests tend to fall into different patterns according to Nobel group. One particularly interesting pattern involves the unexpectedly high rate of science training and avocation among non-science Nobel laureates. For instance, 87% of laureates in economics, shown in purple there, have formal education or persistent avocational interests in the sciences, mainly focused in mathematics, but also in physics and, wait for it, psychology. Given the importance of mathematical modeling to much of economic theory, perhaps these scientific interests are not so surprising, nor is the interest in the psychology of decision-making and related subjects. However, we certainly did not expect to find that 24% of winners of the Nobel Prize in Literature, in pink, also demonstrated strong interest in one or more sciences, or that that figure was almost 20% for Peace Prize winners, shown there in yellow. Maurice Allais fits the interest pattern of economists to a T. Trained in the sciences and engineering as well as economics, he maintained throughout his career two simultaneous parallel interests, one in economics and another in physics. In fact, in physics, he received almost as many honors as he did in economics. This twin focus gave Allais, quote, valuable experience reflecting on the nature of our knowledge, the nature of experience and theory, the difficulties of experimentation and the interpretation of results, and the scientific method in general, end quote. He found a useful cross-fertilization of analytical methods from physics to economics, all of which fed his preoccupation with synthesis across the sciences and social sciences. George Bernard Shaw, Nobel laureate in literature, provides yet another example of the non-scientist integrating science into his concerns. Shaw was an extraordinary playwright, a polemicist and political activist, a music critic, and an excellent photographer, as illustrated by the self-portrait you see here. He was also a self-described, quote, scientific biologist, or as he sometimes called himself, a meta-biologist. Indeed, his work, Back to Methuselah, a meta-biological Pentateuch, consists of a series of 5 plays that explore the evolution of humankind through a moral biological lens, asking, among other things, the science fiction-like question of what would happen if scientists cured us all of aging. Many of his other plays were similarly influenced by his biological studies. Scientific training also often fostered the success of Peace Prize winners as well, as illustrated by Fridtjof Nansen. Nansen was a great athlete in his youth, winning the Norwegian skating championship, breaking world speed skating records, and finishing first in an annual cross-country skiing race for 11 years in a row. He subsequently used these physical skills in polar expeditions undertaken as an explorer and oceanographer, during which travels he also made use of his artistic avocation to record his experiences. Nansen was also an early adopter of the new at the time neuron theory espoused by Golgi and Ramon y Cajal, and he later incorporated his science into his rationalist philosophy of life. Finally, in what amounted to a second career, he parlayed his extraordinary prominence as an explorer and a person of unusually broad culture into the diplomatic peace initiatives before and during World War I that won him the Nobel Prize. Getting back to the broad strokes, we found yet another interesting and rather unexpected avocational pattern. A majority of the Nobel laureates in the sciences had formal training in more than one science. Far from specializing, the typical Nobel laureate trained in 3 scientific disciplines and worked at their intersections. In fact, over 50% of Nobel laureates in the sciences pursued multiple vocational and avocational interests, both within the sciences as well as outside the sciences. Their polymathy was deep as well as broad.
So let's take a moment to see what this deep and broad multidisciplinary integrated interest within primary professions might look like by actually visualizing the publication patterns of scientists in the IDESON project that I mentioned earlier. The top 6 ribbons here illustrate publication patterns of the most successful, highest impact scientists in the IDESON group. Recall that these individuals were inducted into the National Academies of Sciences and several won Nobel Prizes. The 6 ribbons at the top are 6 of the, at the bottom are the 6 study participants who had the least success and the least impact as scientists. You can see here we have put up the first 100 papers of each individual, if they publish that many, denoted by the numbers 1 to 100 above the ribbons, and each color represents a different research subject. So you're going to notice that the very successful scientists have very colorful publication records. They kept jumping between many different areas and research topics. In contrast, look at the very low diversity of the research subjects exploring that were explored by the low impact scientists. Most of these individuals rarely strayed from their graduate training and sometimes stayed completely within one research area. Quantitatively, the highest impact scientists explored an average of more than 6 research areas during their careers and published over 400 papers, constantly investigating several simultaneous fields and going back and forth between them. By contrast, The lowest impact scientists explored an average of only slightly more than 2 research areas and very rarely changed from one field to the other. Now, notably, the scientists in the Idison study were aware of the types of strategies that they employed. Which brings us to our 4th theme, the individual polymaths' perception of the connection between their interests. The highest impact scientists were always interested in everything, combining multiple skills across many fields of learning. And for these scientists, everything they did tied into their work in some way so that even their leisure time activities became grist for their creative scientific mills. Some of the highlights: I was always most interested in anything. I have a big tendency to use my hands, and I also have a tendency to use my intellect. Well, the scientists are a great way of combining those operations. Another, who was, of course, a musician and a geologist, says, suppose someone's getting interested in musical problems. He may then apply what he finds there back to his scientific research. Now, in contrast, the lowest impact scientists, when they had avocations and hobbies, which was less frequently, always thought of them as detractors from their scientific productivity. And here are some of their highlights. I don't try specifically to develop hobbies, since all these things take away from one's creativity. They're just excuses not to do the work. Very different approaches. Now, like the top scientists in the Idison project, Nobel laureates also find creative connections and applications between their various interests. Nothing they do is a waste of time. Take Hermann Hesse, the laureate in literature who took up watercolor painting in midlife. The art soon became a consuming avocation. Without painting, he confessed, I would not have become, or would not have come so far as a writer. Painting had, quote, a similar tension and concentration to writing for him, which involved keeping in mind what is not yet painted, what is invisible, quote, to the whole picture, end quote. The skills and the techniques of one art fertilized the other, and vice versa. Everyone probably knows that Einstein was not just a physicist, but also a musician. What often gets forgotten is that he himself attributed his scientific success to his music. The theory of relativity, he wrote, occurred to me by intuition, and music is the driving force behind that intuition. My new discovery is the result of musical perception. Elsewhere, he said of the theory of relativity, it is the result of musical perception. Now, the ultimate integrator that we found so far may be Herb Simon, yet another Nobel laureate in economics. Simon was as much a computer scientist, cognitive psychologist, political scientist, and philosopher as he was an economist, albeit one driven to integrate all of his interests. In his autobiography, he referred constantly to the excitement and pleasure he derived from the transfer of techniques and tools from one field to another. And not just in its professional activity. Significantly, he also devoted himself to many hobbies, or as many hobbies as he did to his academic disciplines. These avocations included chess, piano playing, musical composition, drawing, and painting, all of which his colleagues said he could have done at a professional level. Each one became grist for his mill, which was understanding the cognitive foundations of decision-making. Quote, I can rationalize any activity I engage in as simply another form of research on cognition. I can always view my hobbies as part of my research, end quote. And to view all these activities as part of one grand whole was in fact the point. Simon consciously integrated his multiple interests and activities into a singular focus. Quote again, the Renaissance mind, he argued, is not broader than other intelligent minds, but happens to cover a narrow swath across the multi-dimensional space of knowledge, end quote. In his case, the controlling purpose or problem was decision-making. For him, as for others, vocational, avocational polymathy became a deliberate strategy for maximizing the potential for creative success. So to summarize, our progress thus far shows that polymathy involves integration, and integration is the key to creativity. The polymath connects and integrates his or her interests in such a way that experience with disparate skills, ideas, techniques, and problems is maximized and available for reapplication. Think of Nansen combining his athletic skills with his scientific interest in polar oceanography to become one of the most successful polar explorers of the 20th century. Think of Hesse with cross-fertilization in his writing with his painting. Think of Hodgkin honing her visual skills, which were found necessary for X-ray crystallography by drawing intricate structures such as mosaic patterns for her parents and insulin molecules for her work. Put another way, creating means inventing and resolving challenges in new and effective ways. So creating depends on the ability to combine and integrate disparate ideas, materials, techniques, skills, and so forth to find promising new problems and then explore possible solutions. Every creative insight involves first identifying our ignorance and then putting together what has not been put together before to address it. So to a profound degree, creating depends for us on polymathy.
So let's take it as a given that creative polymaths depend on finding and exploring connections between interest areas. But what enables them to do this? With Theme 5, we look at the mental skills, some of the mental skills, that encourage cognitive connection making. In his 1989 book, Discovering, Bob investigated what eminent scientists had to say about their ways of thinking. The result, he found, was a mental toolkit made up of skills such as observing, imaging, abstracting, and patterning, but also including ways of thinking that he, Bob, had never run across in any of his own scientific training, things like empathizing with the subject of one's study, or embodying equations or other aspects of a scientific system into your body, playing, literally, for the fun of exploring possibilities, and so forth. Now, whenever Bob would come home and tell me about these odd ways of thinking that he was finding out doing all his research, I would invariably respond with an equivalent example from my own studies of dancers, poets, novelists, or artists. At some point, we realized that not only are most creative individuals polymaths, but they use a common set of mental tools for integrating their vocations and avocations across disciplines. This concept of tools for thinking became the theme of our 1999 book, Sparks of Genius. We don't have time to explore all the tools for thinking here, but we do want to give you a flavor for how these can be used to link concepts and methods across the disciplines and also function as a common language linking the disparate disciplines. We'll consider 4 tools. Let's start with one of the most basic, observing. Observing means honing all of your senses to perceive acutely and accurately. The painter Georgia O'Keeffe looked carefully at things, and she forces us to do so too in her very large painting of flowers. Still, in a way, she said, nobody sees a flower really. It is so small, we haven't the time, and to see takes time, like to have a friend takes time. Louis Pasteur, the French scientist who gave us the germ theory of disease, pasteurization, the first vaccines, and so much more, provides a case study in how arts can train scientific observing. Pasteur was formally trained as a portrait artist from the age of 12. This portrait of his mother he made at the age of 13. At 18, Pasteur entered college to study chemistry and physics. One of his crystallography lessons was a standard exercise observing tartaric acid crystals, a byproduct of winemaking, and he was supposed to draw what he saw. His professor was the world's expert on those crystals, and thought he knew them thoroughly. Pasteur proved him wrong. One of the first lessons one learns as a portrait artist is to look for the asymmetries in a person's face, as these are often what gives it character. Even the most beautiful faces, such as Marilyn Monroe's, are asymmetries, as these mirror image views of the left and right side of her face mirroring each other demonstrate. Having observed faces for 6 years prior to examining the tartaric acid crystals, Pasteur naturally applied his portraiture practice. He quickly noticed what his professor expected he would notice, which is that the crystals have asymmetric facets. Pasteur, however, also noticed what had never been noticed before. There were 2 types of crystals present, one the mirror image of the other. The professor didn't believe him until Pasteur separated the 2 types out and juxtaposed them side by side. This was the first example ever described of what chemists call handed molecules. We believe that this discovery is a direct instance of artistic training applied to science. The next tool we'll take a look at is abstracting, which means or is a process of discovering simplicity in complexity by eliminating all but one essential characteristic. Picasso left us an excellent example of the abstracting process. All abstracting, he said, begins with something real and then proceeds by eliminating more and more unnecessary detail. At the upper left, he begins with a fairly realistic bull, and then going left to right and then down, he explores which characteristics of a bull are most essential. Is it the mass, the planes, the outlines, the size of the horns, the tail, or the sexual organs? In the end, at the lower right, Picasso decides upon a simple set of lines that suggest bull without actually saying it. For Nobel Prize-winning biologist Nico Tinbergen, abstracting was an integral part of experimenting. Tinbergen studied the behavior of the herring gull and noticed that the chicks pecked at the parent's beak to obtain food. Was smell the stimulus for pecking or something else? Tinbergen made a simple, realistic cardboard model of a gull's head and presented it to the chicks. They pecked at the beak. He now knew that smell was not the trigger. What happened if he changed the shape of the head, its color, moved the red dot, or left it off altogether? What if he simply presented the chicks with something red, like a pencil? In the end, Tinbergen discovered that all that pecking for food could be elicited by anything that was red. Red was the ultimate abstraction of the goal signal for food. And by the way, this photograph of Tinbergen captures him utilizing the next 2 tools we highlight this evening, body thinking and empathizing. Body thinking means using muscle memory, physical feelings, gut reactions, and emotional states to recognize, organize, and address problems. It involves kinesthetic awareness of body position, balance, and movement, of hand-eye coordination and gross motor control, as well as recalled images of body feeling and body movement, all of which can be employed as a kind of physical thinking. Body thinking was of foremost importance to the genesis of Auguste Rodin's famous sculpture, The Thinker. What makes my thinker think, Rodin wrote, is that he thinks not only with his brain, but with every muscle of his arms, back, and legs, with his clenched fist and gripping toes. Artists like Jackson Pollock also thought with body as well as mind. Pollock's paintings can in fact be understood as records of his rhythmic movements around the canvas. Pollock was dancing solo, but what dance partners must learn to do is dance collaboratively, responding to visual and physical cues. As a graduate student at MIT, mathematician and swing dancer Summer Gentry used her artistic understanding of body thinking to address the problem of robot-human interactions. As a dancer, she knew that it is one thing to make a robot that can mimic the individual motions of a human being. In that center image, you see that happening. But it is quite another to invent robots that can respond to haptic, touch-based signals as human partners do. In 2002, she programmed a robotic arm to lead blindfolded dancers through a series of dance moves by touch alone. Her far-off goal? To design robots who can signal move changes in advance and can also respond to haptic feedback from human partners, thus setting the stage for improved robotic surgery and other applications. Empathizing means becoming the thing you want to understand or recreate in a Zen-like integration of self and other. It means putting yourself in another's shoes, so to speak. Artists have purified the concept of empathizing, taking it in directions that sometimes boggle the mind. One such artwork is Isamu Noguchi's core, a 6-foot-high block of stone with a hole cut into it. "Go ahead," wrote Noguchi, "stick your head into it. Then you will know what the inside of a stone feels like." Think about that. Then you will know what the inside of a stone feels like. Empathizing is a common mental tool in the creative thinking of many of the world's best scientists. Nobel laureate Barbara Mcclintock, one of whose hobbies was singing, studied the genetics of corn, eventually discovering the phenomenon of what are now called jumping genes. She knew her corn plants so intimately that when she was studying their chromosomes, she talked of going down the microscope into their genetic world, where she became their friend and developed a feeling for the organism so complete that she knew each one as an individual. Such empathizing was the creative engine of her scientific insights, which she then translated into the formal experimental language of science. The physicist Jacob Shaham empathized with equations, using skills he had learned in acting class. For Shaham, merely learning how to solve equations was not enough to really understand them. One had to be able to imagine the stage upon which the equations play out their actions, had to be able to imagine how the various characters that their symbols represent would behave under various circumstances. Just as the word "hi," uttered loudly or mumbled quietly, has different meanings depending on context, so too, Shaham felt, do equations have different meanings depending on context.
So, we have now taken our investigations of tools for thinking beyond the personal testimonies of exemplary individuals to statistical studies of various professional groups, primarily artists and scientists at this point. The first two columns of this table demonstrate our comparisons of arts, crafts, and design professionals, labeled art in red, and STEM professionals, labeled SCI in blue, with regard to their thinking tool use. So let's highlight the thinking tools we just discussed. If you look at the asterisks in red, you will see that the artists are significantly more likely than scientists to use thinking tools such as abstracting, body thinking, and empathizing. If you check out the asterisks in green, you see that the artists and scientists are equally likely to use tools such as observing and visual imaging. We also gathered data on the use of verbal and other symbolic forms of thinking, and the only skill that scientists use more than artists is, not surprisingly, logic. But note those black boxes on the top left. All right, overall, these data suggest that arts may prove an unusually adept way at teaching tools for thinking, not only for scientists, but across the entire curriculum. As we've already seen, artists have purified many of these tools into specific ways of thinking and acting. In fact, we've recently completed a very lengthy and reasonably complete review of high-quality, well-controlled studies demonstrating that arts-based curricula are capable of significantly improving a variety of STEM learning outcomes. Among our findings is the very strong evidence that visual imaging ability is one of the best predictors of success in STEM fields. More importantly, a very robust literature demonstrates that training visual imaging ability through arts, photography, sculpting, jewelry making, computer-aided design courses, and so forth, even in the absence of any STEM content, significantly improves scores on visual thinking tests and also on STEM learning outcomes among students of all types, and particularly minorities and women. Less attention has been paid to the role of other thinking tools in STEM learning and practice, such as abstracting, body thinking, or empathizing. Nonetheless, well-controlled evidence exists that these skills too can be taught for effective improvements in science learning, thus corroborating what our study of the individual exemplars has long suggested. Perhaps the best case so far has been made for educational interventions to improve empathizing skill. We've reviewed several studies investigating the use of theater acting techniques to improve empathetic ability for medical students, for instance, and one notable study using empathizing to improve student learning in neurobiology. So to summarize one last time before closing, we argue from a variety of data that, first, creative individuals tend to have multiple interests, often across the science-art divide and many other divides as well. They are polymaths. Second, creative polymaths connect or integrate their interests within integrated networks of vocational and avocational endeavors. Third, imaginative thinking tools such as observing, abstracting, body thinking, and empathizing provide a cognitive bridge for crossing disciplines and languages so that the disciplines can speak to each other. Fourth, these thinking tools can be used to enhance classroom training with transdisciplinary efficacy so that, for example, arts training improves STEM learning. Fifth, this then raises the question, what does this mean for educational preparation for creativity? So, we believe it means this. To prepare our students, we must prepare them to be polymathic, and to do this we need what we think of as a Y-shaped student. Now, many of you have probably heard of the T-shaped student. Lots of depth in one subject, breadth in many others, so that they can communicate. We like the Y, but let's deconstruct our Y shape here. Our Y has 2 arms and 2 legs, not one going down. So we propose that every student major in 2 subjects of their choice, thus delving doubly deep in ways that make sense to them personally. One requirement of these dual majors would be a senior thesis that explores one or more links between these 2 areas of expertise. These links might emerge in any organic way, as subject matter overlaps, common problems, historical or cultural interactions, bridges about using the creative process or tools for thinking, and so forth. The point is to get the students to become explicit about how they connect their different ways and different types of knowledge. Finally, the branches of the Y point up and out rather than a T which goes out to the sides, because we want to signify the idea of the student reaching out into the future and into the areas of ignorance where our knowledge fails. This is where the great challenges are. And we need to train our students not only in what we know, but also in what we don't know, how to question and ask about our ignorance and make it explicit. Now, this type of training obviously has many implications far beyond what we can cover in just this lecture, but we wanted to show you that it follows directly from this whole idea of polymathy and integration. Furthermore, this Y shape is a pun, which we want to emphasize, on questioning, because it is a pun about why, The Y-shaped student is always asking why, and also how, and what, and everything else. And it identifies what we still don't know so that they can prepare for the future. As George Bernard Shaw himself, a model of the creative polymath, advised those who would listen, we want students who, quote, don't see things as they are and just ask why, but ones who can also dream of wonderful, better things and ask why not. Creativity should lead to innovation at the hands of entrepreneurs. Now, Shaw, you will remember, was a true polymath. Indeed, when questioned about his reputation, he once explained in exasperation, which reputation? I've made 15. Moreover, he criticized at least one biographer for failing to recognize the connections between his different varied interests. The biographer had a separate chapter on each thing he did. He says, you're still a bit in the 19th century in respect to arranging religion, politics, science, and art in brain-tight compartments, mostly incompatible and exclusive. They don't exist that way at all. In human nature, he said, they are all mixed up in different proportions, and that's how they're mixed up in my plays. If you can't see that, you don't see what I'm doing. All of which is to say, polymathic interests connect. And they connect creatively. In Shaw's case, that creativity continues to inspire us today because his work tells us something profound about the integrated nature of humanity. We would do well to listen. So we'll leave you with one final polymathic exemplar, also worth listening to, and that's Roger Sperry. He was a scientist-artist to Shaw's artist-scientist. Sperry won the Nobel Prize in 1981 for his research on split brain capabilities, describing in detail the specializations of the right and left hemispheres of the brain. We all now talk about right brain and left brain characteristics. It's become part of our popular culture. And yet Sperry was very upset at this. He himself never stopped arguing that the intact brain, not the split brain, but the intact brain is ambicerebral, and that the whole mind is greater than the sum of its hemispheric parts. In light of our own research over the last 30 years, we take this as a call to arms, to advocate for whole mind education, one that prepares individuals to connect and integrate different disciplines and different kinds of knowledge in fluid and flexible ways in order to meet the challenges of today and invent those of the future. Creative polymathy, we believe, is a personal and social good worth striving for. Why not? Thank you.
Questions or comments from your...
Well, we're glad you all agree. You're now going to all go off and do this. Yeah.
How can you tell that the success of these people is not...
Oh, good. That'll help.
Is because of this polymathy that they have, but not because they're simply just smart and curious people?
Yeah, that's a question we get asked frequently. So the really important stuff is that we've shown that this is trainable. That's one of the studies that we did when we were looking at whether arts, for example, can improve STEM learning. The whole point was to look at if you're not an artist, you don't know how to draw, and we give you lessons in this, does this improve your ability to think visually, model things, and so forth, and then does that transfer over to your STEM learning? And it does, and we can do that with there are studies with virtually any combination you can make. So that very strongly suggests that maybe even if you know the most great genius is talented and born that way, nonetheless we can learn the lessons of how they operate in their mind and contribute that to everybody.
You seem to have suggested this subset of group, the Nobel laureates. But there's a whole vast world out there
Sure.
with lots of very brilliant-minded people. And so, let me give you an example. Mahatma Gandhi, for example, he was not a polymath to my understanding, and he brought this notion of non-violence to the world. Or for that matter, the brilliant athletes, they specialize in just one thing, and they are recognized for what they do. So I'm just wondering, why is this notion of polymath that critical in the development of a human being?
Well, one of the things is, yeah, people bring up that objection a lot, and in the creativity field, some people will argue that you can only look at polymaths who are professionally doing like two or more things on a professional level. Those are the real polymaths, those are the real geniuses. What we're saying is that you can be a polymath even if you have a profession, then you might have some side interests that you never develop to a professional level. They're just hobbies for you, but they can be critical to giving you ideas for your profession. Or they're critical just to giving you the relaxation that you need, but often people will start being fed skills and other things that they need in their profession. And that does open the door to way beyond the Nobel Prize winners or way beyond people who have dual careers. Now, I really don't know the biography too well of Mahatma Gandhi, but I would suggest that if one looked at his biography or a great athletes, you begin finding that these people often have other interests, and they see connections, or they're important to them and they won't give them up for certain critical reasons.
The other aspect here is we're talking about creative. I mean, one of the things we put up was creative polymathy. Okay, so yes, you could have Usain Bolt, who runs really fast. He's the world record holder in various sprints. He's probably not a polymath. I don't know one way or another. All he has to do is run really fast and be really well trained. Okay, that's a very special thing, but he isn't inventing anything new there. And so this is one of the really important things that we look at. You might be the best in a very well-defined field by being extremely specialized and narrow. We're perfectly willing to admit that. But the chances are that you are going to transform your field, invent new fields, open up new possibilities for humanity is probably fairly small, which is why we'd think that Gandhi probably has a very interesting background, and he'd definitely be worth looking at. It's very unlikely that a person simply sits down one day and says, well, everybody is fighting, I'll just sit down and that's it. You have to have a philosophy, you have to understand politics, you have to have all the skills in order to motivate other people and so forth. And it's very unlikely those were developed just by doing one thing well from the time he was 5 or something like that. We're not saying that a person who plays a Bach concerto extremely well has to be creative. Technically, you may be able to do that, and that's very successful within music. But they're not the ones that are transforming music. So that's really the difference. So many forms of success, we're looking at one, and it's specifically at these creative individuals. And the reason we're doing that is very simply we're looking at a future where transformation is so quick, and the specialization is getting so early that we think there are people just not able to see the breadth of problems, real world problems today. I think if we look at healthcare, we look at politics, we look at anything, none of these are being solved by the experts. I don't think they see the entire range of what the problems are. And I think that's what we're trying to correct to some degree. You could overdo it. It probably wouldn't make sense to make everybody a polymath. That would also probably be just as bad as everybody being a specialist. But right now, we don't train polymaths. They emerge more or less on their own against the grain of the specialist training that we do.
Yeah, so your Y-shaped student ideally is able to double major in 2 subjects. For a lot of the rigorous science disciplines, that is not functional, and it would push students to the verge of like collapse. So what do you say is like a functional solution? Yeah, seriously, and especially in engineering too.
I'm a scientist. I understand exactly
Yeah.
what you're saying. I think because our science training is completely inappropriate. So,
Yeah, so
I have an undergraduate degree in biochemistry. I have an international reputation in 3 different sciences. I have no formal training in any of them. Okay? You don't need to have a PhD in every field you work in and be able to grasp all the details. What you need to understand is what you need to learn. And in fact, the key that I found, and this is what I do when I do consulting for major corporations, is get them away from specialization to look at the problem. So this is a whole different area. We haven't talked about this at all here. Problem-directed research is what works. This is what these Nobel Prize winners are doing. They let the problem tell them what they need to learn and how to learn it. Okay? So once you have grasped the basics of a subject and you know how to learn something deeply, the problem tells you what you need to know, what kinds of skills you need to bring to it, and that's what we need to be teaching students to do. Now, I do this, and I actually have a colleague at Michigan State who studies this formally. We have stripped our introductory biology courses to about 1/3 of what most introductory biology courses are. When students move from our programs to other universities, they do not get credit for these courses because everybody at other universities looks and says, you only covered 1/3 of the curriculum. I mean, your students obviously don't know enough. Well, our students outperform everybody else in the university in all the science classes they take. Because what we do is we teach them very rigorously this small amount of stuff, and then we show them through principles how it can be applied to the rest and say, if you're interested, go learn it. Because you now know how to learn what it means to master something, and when you get to your next course, you'll do this. So I've taken non-majors who have no background. They had a non-majors introduction of 3 weeks of genetics in my classes who outperform zoology majors with 2 years of genetics. Because the way I teach the genetics is so much more profound, it's so much deeper, and it's so much more based on just basic principles that they know how to solve any genetics problem. And they go off to these classes, and that's what they do. The rest of the students are learning it by rote. They're just memorizing everything. Every problem is a new problem. They don't see the connections, so they know a huge amount. But you give them a new problem where they don't understand the principle, they can't apply it in any way. So part of the whole Y-shaped student is based on changing other aspects of education as well. That's why, I mean, we could have given a whole talk on Y-shaped students, but then you wouldn't have known why we were talking about a Y-shaped student. It becomes a chicken and egg problem. But yes, it's a great question.
It's kind of the next stage for us as well, the Y shape. You know, it's kind of a current thing.
So,
Do you want to go somewhere there?
Go ahead.
Okay. You mentioned that one statistic about the Nobel Prize winners tend to be like twice as like polymathic as like other successful scientists. And I was wondering, have you considered like the effect of like the political aspect of Nobel Prize? So maybe their polymathy helps them communicate their results better, or
Sure.
like their visibility. Have you thought about that at all?
Yeah, that's definitely part of what's going on. So we used to have a slide which basically said that artistic scientists had more imagination, an image in their imagination. Musical scientists could duet better. I mean, literally, they are better at collaborating. The literary ones are better at communicating. These are oversimplifications, but that's certainly part of the skill set that people get. So there are a fair number, when you look at people who are really great lecturers, a lot of them have training in theater and things like that somewhere in their background, and that makes perfect sense. They're comfortable getting in front of an audience, and they learn techniques to manipulate them and get them excited. So yeah, that's definitely part of it. Many of the Nobel Prize winners write very explicitly about, the most important class I ever took was my 11th grade English, because I learned how to write clearly. And then they can tell you how that's been a benefit to them compared to their colleagues who may be doing just as good a research, but nobody can read their stuff. I had a really interesting experience as a postdoc where I saw this in action. So Linus Pauling, who had the Nobel Prize for figuring out bonding between different molecules, and a woman crystallographer who worked in the same area came to the Salk Institute. They both gave talks. As far as I know, they were on the same subject. I thought I understood everything Pauling said. I seriously doubt that I did, but he communicated it in a way that made me think that I did. And the woman gave a talk which was so abstruse, I hadn't a clue what she was talking about. And it turned out that's basically what the entire audience got. There were maybe 2 people in the audience who had the technical expertise to follow the woman's talk. Everybody else thought, oh yeah, Pauling's nailed it. He's got, and then of course afterwards realized, well, maybe we didn't really quite understand all of the nuances. But that was, clearly that was part of what made him a Nobel Prize winner.
I know there was a question over here.
Hi, you showed the figure with the first 100 publications of the high impact scientists and then the lower impact scientists. If you had time as a component of that figure, is there a significant difference? So are polymathists slower? So the time it takes to get to your first 100 publications, do you find?
So yeah, there was certainly a significant difference in the time to get to the first one. The Nobel Prize winner type people were publishing probably 3 times as many papers per year, right from the start.
So they're faster.
We did look at age. The age at which they started was irrelevant. I mean, there were people in the lowest group who started publishing at 18 and people in the highest group who had their first publication at 30. There were some really striking anomalies. So one of the ones in the top group, which you may or may not have noticed, the last one in the group, had only 79 papers. He also had the highest diversity of anybody. That was Richard Feynman. And every one of his papers is a citation classic. I mean, I don't think he published anything that had less than several hundred citations. And he had something like 30 or 40 that had over 1,000, a couple over 10,000. He published very little and only on things that he knew were earth-shattering. So total number of publications, we did actually look at that. That is not a correlate. The number of publications you have does not correlate with, so if we looked at the middle groups, there were lots of people in the middle groups who had more publications than the Nobel Prize winners, but nobody ever cited them. The most, in fact, my father knew the guy in computer science who had the most publications of anybody in the field. It was something like 1,300. The total citations for those 1,300 papers at the guy's death was about 570. In other words, he didn't even cite his own papers. So just churning the stuff out doesn't necessarily get you anywhere.
Right.
Okay. I would like to pause now and thank everyone.